to the cloud. So find the inverse function. That's a pervasive typo right there. Now my Apple Pencil doesn't want to work. Crying out loud. That's an easy fix. Yeah, it should be find the inverse function and then graph both. When it comes to creating a graph, the general rule of thumb is you could do it with Desmos, you could do it by hand. It's up to you. I don't have any particular requirement in terms of the method that you use to create a graph. All right, so find the inverse function of that thing. All right, so f of x is equal to x squared minus 4. First step in the process is we replace the f of x with a y. All right, then we switch the x with the y. All right, so x and y swap for one another. So x is equal to y squared minus 4. Then we're going to solve for y. All right, we'll do that by adding a 4 to both sides. So we have x plus 4 is equal to y squared. And then I want to get y alone by performing the opposite operation. I have a power of 2 to undo a power of 2. I take the square root. So I'm introducing the operation of radical, the square root. And so when I take the square root of any number, the result is always plus or minus. All right, so I have to include that as the appropriate sign, because if I take the square, any calculator will lie to you. They'll tell you the square root of 4 is 2. But if you test it out, we say 2 times 2 is 4. Yeah, that's true. But also negative 2 times negative 2 is also times negative 2 is also a positive 4. So when I take the square root of a number, I have to account for the negative one as well. All right. So that's why we tack on the plus or minus in front. And that's going to become a recurring theme in this course over and over and over. So you've probably experienced some of that in college algebra, or whatever algebra class you took. But what's going to happen is we're going to see this rear its ugly head in just about everything we do in this class, this plus or minus idea. All right, so we got to learn to accept it. So what I'll write using the proper notation is f with a little power of -1 of x, that means the inverse function, is equal to plus or minus the square root of x plus 4. All right, now it's kind of a weird situation because this makes it seem like we're dealing with just one function, because we write it as f inverse of x, and it's like, oh, that's just one function, but it really isn't. It's 2 separate functions that are pieced together. All right, so it's just a shorthand way of representing it. Right, so what this means is that f inverse of x is equal to negative the square root of x plus 4, or f inverse of x is equal to the positive square root of x plus 4. All right, that's the interpretation. You only need to write this as a final answer, but those other things are the true meaning of the plus or minus square root of x plus 4. All right, so if I want to create the graph, I type in my original function. All right, so we got that. Then I type in my inverse function. Now, I'm going to actually try something. I've never tried this before. I just wanted to see. You never know. Sometimes Desmos surprises. It would have been nice. I just wanted to see if it would actually graph the inverse function for you without you having to come up with the equation. Right. So then I would graph y equals the square root of x plus 4, and then do it again, but with a minus sign. All right. So that little gear icon, again, that's your duplicate. You hit the gear and then you hit that little double page icon. That'll allow you to duplicate a line, and then I just slipped in a minus sign in front. Right. So what we're looking at here is essentially, if you piece the two parts together, we're looking at a sideways parabola. Right? Well, it's a parabola. It just happens to be sideways from our perspective. All right. So this is what our graph would look like. And if you wanted to submit this on, as your work on a test, you would just need to put in some labels, all right, to indicate which one is the original and which one is the inverse function. Right. So, because, if you think back to, any kind of instance in the past where you had to create a graph, almost always you had to have some kind of labeling, right, in order for it to be an appropriate submission. Right. So first off, I'd want to label my x and y axes. So for the x-axis, I'll type in x. Y-axis, I'll type in y. It could be lowercase, uppercase, doesn't matter. It actually kind of matters, but it autocorrects to uppercase. So I don't want people to worry about losing credit for stuff like that. So you can just leave it as upper. But if you take it off the cap lock and don't let it autocorrect, then you can make it lowercase like it ought to be. So that's fine. And no matter where you position the graph, the y and x will stay in its relative location. That's good. Now we just need some way of labeling the graph. Now, when we create a label on Desmos, it's kind of annoying because we could do it for coordinates, but it's not easily done for functions. So for example, if I typed in the coordinate 1, 2, I can tap on label and then type in a label, all right? So if I long press on this icon here, you see that these are the only options that we, aside from that copy business, I don't know why that happens. All right, long press, okay, well, whatever. These are the only options that appear. I'll just say copy. We can impact the thickness, we can impact the color, but we can't label anything. All right, we can turn off the equation if we want, but that doesn't help. All right, so what we would do is pick a point on the graph and plot a value. All right, so some point that you know is definitely there. Like for example, I mean, it's just an ordinary x squared minus 4. So if you plug in a value for x and solve, you'll get an answer. But you can also just kind of drag along and see if there are any clean coordinates. There's definitely a clean one here, but I kind of want something towards the tail end of it. Something up here, So what I would do here is I'd say that I want to plot 4, comma, and then I'd plug in the 4. So 4, 12. Produce the label there, but then change that label to f of x. All right. And then just hide the point. Just tap on the point. For some folks, this is more trouble than it's worth. You look at it and say, well, okay, I'll just do it by hand because I'd rather do it by hand than do all this stuff. I mean, I understand. But what you could also do, and so it gets kind of nifty if you really start thinking this through, you can type in, instead of 4, 12, type in 4, f of 12. I'm sorry, 4, f of 4. What that'll do is it'll evaluate the function by replacing the x value with a 4. So it'll compute it for you. So that's kind of nice. All right. So once you've labeled your f of x, you're good, because the other function or the other graph must be your inverse. So I'm fine with, as long as you label one of them, you're good. But if you want to label the other one, then just grab a point that you know is on that graph and plot it, and then do the same thing, right? The only issue that you're going to run into, well, among other things, is you're not going to be able to get that power of -1. So I look at it as like, why even bother then? If it's not going to look the way it should look, then don't even bother. As long as you got one of them labeled, it's implied that the other one must be the one that you're looking for. Or the other one must be the inverse. I don't even know why I said what I just said. I have this tendency, you've probably noticed it, to just speak and sort of hope what I'm saying makes sense. Doesn't always play out, unfortunately. So I just pop this in here and we're good to go. All right. But like I said, if you want to make it by hand, go ahead and make it by hand. Okay? And for some people, what I'm showing here is enough evidence for them to say, yeah, okay, I'll just make it by hand. Because I don't want people to go into the test not having a plan. Like if you don't know that you don't know what you need to know on Desmos before you take the test, then you're going to be in a pickle. All right. I like pickles. Claus and pickles so far have been the winner in the best pickle department, as far as I'm concerned. So if anybody's in the market to try some new pickles, Clausen at your local supermarket, give it a shot. You won't regret it. I also don't mind the Stu Leonard's pickles in the refrigerated section, but you know, like the Clausen you get anywhere. That's why I go with that. All right. So for number 4, part A is pretty much what we've been doing. Part B, that's going to be a new step, and it's going to involve a new rule. All right. So algebraically find the inverse. Okay. So step 1, write it in terms of x and y. So y is equal to -1/3 x minus 2. Swap the x and the y. Solve for y. So I'm going to add 2 to both sides. So x plus 2 is equal to -1/3 y. Then if I want to get y alone, I'll just multiply both sides by -3. Clears out that denominator. You could also divide both sides by -1/3. That's up to you, but they both accomplish the same thing. So we're looking at y is equal to -3x minus 6. And just using the appropriate notation, we would say inverse of f of x is equal to -3x minus 6. All right. So that's all just kind of a continuation of the stuff that we've been doing. Nothing new there. Part B, that's a little bit more interesting. All right. So it's going to involve the composition of functions. That old topic. So we'll learn a new rule and apply that rule, but you'll see that the outcome should be exactly the same in every case. So you kind of know going in what you should be on the lookout for. So so yeah, let me give you the rule as soon as I open up this Jolly Rancher. So the rule f of the inverse of f of x is equal to x. All right. If that's true, then
What's that sign in between F and F inverse?
Oh, that's an and symbol.
Okay.
At least it's trying to be. So if f of the inverse of f of x is equal to x, then those two functions are inverses of one another. Which actually seems kind of like redundant, I guess. When I say f inverse of x here, it's implied that what I'm saying is the thing that I'm claiming is the inverse. We don't know for sure, otherwise we wouldn't be testing it. So f composed with the assumed inverse, if that is equal to x, then we will have confirmed the relationship. All right, so let me show you how it works. So using our stuff from part A, f of x is equal to negative 1/3 x minus 2. Our assumed inverse, because we did the work, is negative 3x minus 6. All right. What this property or this rule is telling us to do is take my inverse function or my assumed inverse function and plug it into the original function everywhere I see an x. All right, so I'm taking my assumed inverse and plugging it into my original function everywhere I see an x. So I'm going to take that f negative 1 of x and plug it in. And then in turn, I'm going to swap that f negative 1 x out for what it really is, which is negative 3x minus 6, or what we assume it is. Then we simplify. And if we come up with anything other than an x as a result, then these two functions were not in fact inverses of one another. All right. So distribute. I'm looking at x plus 2 minus 2. 2 and negative 2 cancel away, so we get a result of x. All right. So we would say that it is verified. Right. That's all we have to do. I mean, conceptually, it's a pretty big idea, but the act of carrying it out isn't that bad. Right. So again, it's just a composition of functions. We're taking one equation or the expression and replacing all the x's in the other function with that expression, simplifying, and all we're looking for is an x.
Professor, can I stop you for a moment?
Sure.
If you don't mind. Part A, I have always personally struggled with fractions. So if maybe you can get through to me here. Like you have in red, x equals negative 1/3 y minus 2, right? I understand that you added the 2, and then you get up, and then now you have a negative 3 out front. Can you please just explain that whole thing, negative 3 with the whole, that whole line that you're on right there? If you don't mind explaining that, I'm gonna get lost and it screws me every time.
Not a problem. So what I want to do is I want to get rid of the y. I'm sorry, I want to get rid of everything except for the y. I want to keep y. So I want to isolate this. In order to do that, I need this fraction to go away. All right. So what I'm looking for is what I could multiply by that fraction in order to make it equal to a 1. All right. So what we do is we take the reciprocal of the coefficient. So these two are reciprocals of one another. if we multiply by the reciprocal, the result will always be equal to 1. So what we did was we had originally a -1/3. We took that, multiplied it by a -3, which makes it a 1. A 1y is the same as saying y.
So it goes away.
So it goes away.
Okay. And then you have to do the same thing to the other side of the equal side. Okay, we learned this last year, but for some reason, like the professor just made a big mess.
Fair enough.
Okay, thank you.
Professor, I'm sorry. I gotta restart my computer. My screen keeps freezing. So if you see me leave, I'm gonna pop right back in.
Okay. Thanks for letting me know. So that's the concept of an inverse, and you can apply that same principle, the whole composition thing with really any of the problems that we did, just to verify. But it'll always play out the same way in the sense that we're looking for x. All right. So in fact, like while I'm here, why don't we take this funky one? Let me just shrink this down a little bit. Okay, and let's say we needed to verify. Again, we have f of x is equal to x squared minus 4, and we have the inverse is equal to, we said plus or minus the square root of x plus, whatever there. All right, so to verify, we would find f of the inverse of x, of f of x, which means that everywhere I have an x in my original function, I'm replacing it with the inverse. All right, the inverse is the inverse. The inverse is the inverse. That's fun. The inverse is f inverse of x. Which simplifies when I put the plus or minus the square root of x plus 4 in there, simplifies nicely, because if you square, and people have gotten confused about this one in the past, so I'm explaining it hopefully pretty carefully. If you take a negative number and square it, the result is always going to be positive. Take a positive number and square it, the result is always going to be positive. So, for example, if I have -2 and I square that, it's a positive 4. If I have a positive 2, I square that, also a positive 4. Bottom line is, the act of squaring makes the signage irrelevant, right? The fact that it's plus or minus no longer matters because it's going to automatically be positive, right? So the next step in this process would have this becoming x plus 4 minus 4, because if you square something that's already under a radical, it releases the expression from the radical. So, for example, if I had, let's say, the square, keeping it simple, the square root of 4, if I then take that and square it, you see how the answer is the thing that was under the radical to begin with, right? So, and you could do that for any number, even if that number involves a variable. So x plus 4. So we have x plus 4 minus 4. The 4 and the -4 will cancel out, leaving you with just an x. And so this is verified. All right. So you can see here the technique, even though it involves powers and roots and stuff like that, it still is the same technique. And you're still looking for the same result. It's just how you get there is slightly different. Right? And obviously, the more complicated the expression, the more arduous the algebra is going to be. So let me stop this recording.